All right, we'll get some of this stuff out of the way. So today we're going to be looking at the common base amplifier. Okay. So the ultimate goal is for us, let me write this here. So our ultimate goal is to be able to analyze the following circuit. So I'm going to put VCC over here. This is going to be my resistor R1. Here's my resistor R2. Here's my collector resistance RC. Here's my emitter resistance RE. And then I'm going to apply my input signal through some capacitance CN. So here's CN, R sig, and V sig on this side, and I'm going to take my output at the collector terminal. So here's C out, some load resistance RL. Here's where my output voltage is measured, and this is VCC. So any amplifier in which we apply our input signal at the emitter and measure our output signal at the collector is a common base amplifier. Just like I talked about when we talked about the common emitters, whichever one we wind up not using for inputting a signal or measuring a signal is the common to the other terminals. So this is why this one is a common base, because we're not applying anything at the base. We're not taking our output at the base. For the, I didn't put the arrow here. For the PNP representation of this circuit, it's going to be almost the exact same thing, except our input would be on top and our output would be on bottom, and the resistors would change symbol, but incredibly similar thing. Okay. So this is our ultimate goal. We are going to break it down into smaller, more digestible parts, just like we did with the common emitter amplifier, see how those work, and then see if we can build a model from that. So the base common base amplifier, or the most simplistic version, would be something like this. Okay. So this is the common base core. Where we would have our supply voltage, VCC, some resistance RC like so. I'm going to take V out here. I'm going to apply V in here. And then our base terminal is literally just at some DC. So what we are neglecting here effectively is the contribution of the resistance R1 and R2 and the contribution of this resistance RE. The signal resistance, that's always going to wind up being a voltage division relationship. We're not loading this thing either, right? So this is the most simplified thing that we can do. It's unloaded and it's neglecting some things. So This particular amplifier's small signal model should look something like this. So my base terminal is going to be at an AC ground. Here's R pi and V pi. VM V pi in parallel with our early effect resistance R naught. Here's our collector. We're going to have a resistance RC between the collector and AC ground. Across which we're measuring our output voltage. So I'm just going to put V out over here. And then our input signal is applied between the emitter terminal and ground. So something like this. So here's our small signal model before we move on to analyzing this thing. Does anybody have any questions whatsoever about why our small signal model looks like this? Nobody's piping up, so I'll assume you're okay with this being correct because it is. All right. So much like before, we're going to figure out what the voltage gain is, what the input resistance is, and what the output resistance is so that we can get a model of what's going on. So determining our voltage gain, the first thing that I want us to do is, yes.
Subscript on the left-hand side, that's RL at the top.
RC. It's just a shittily drawn C. So that is an RC because that resistor is placed between the collector terminal and AC ground. So I'll make this C look more C-like, but it was a C all along. Okay. All of those subscripts are literally just based on the positions of the resistor. So when a resistor is connected between the emitter and ground, it's RE. All right. Any other questions other than me having shit penmanship today? Probably every day, but anyway. All right. So what I want us to figure out from the jump is what the relationship between Vn and V pi is. Anybody have any thoughts? Exactly right. So V pi is just equal to negative Vn because the positive polarity terminal of the input voltage is at the emitter node. The negative polarity terminal of V pi is at the emitter node. The negative polarity terminal of Vn is at ground. The positive polarity terminal of V pi is at ground. So the exact same voltage, just of opposite polarities. Okay. So now we're going to apply Kirchhoff's current law at our collector node. Okay. So at the collector, we are going to have a current of, so let me write this down. So KCL at the collector, we have our dependent source current. So that's going to be GM times negative Vn. To that, we're going to add V out minus Vn divided by R naught. And then we're also going to have V out over RC is equal to 0. So I have a single equation. Everything is already in terms of V in and V out, so there aren't going to be any terrifying substitutions or anything like that for this one, which is great. We can all follow along pretty easily. Okay. So all I'm going to do now is move all of my V in terms to one side of the equal sign, all of my V out terms to the other side of the equal sign, and we can see pretty easily that since everything is negative V in on one side and positive V out as it is right here, we're just going to have nice positive coefficients for everything as well. So rearranging this guy, we're going to get something like Vn times 1 over R naught plus Gm is equal to V out times 1 over R naught plus 1 over RC. And from this, our voltage gain can be expressed as the ratio of V out to V in. So that's going to look like 1 over R naught plus Gm divided by 1 over R naught plus 1 over RC. Recognizing that both of those represent the sum of conductances, we can flip things around into resistances. And so this is going to look like R naught in parallel with RC divided by R naught in parallel with 1 over Gm. Now, I've mentioned to you previously that R naught is usually going to wind up being the largest resistance in our system. 1 over Gm is typically the smallest. So R naught will overwhelmingly be significantly larger than 1 over Gm. So this means that this is approximately going to be equal to just Gm times R naught in parallel with RC. And I'm going to write out here explicitly for 1 over Gm much less than R naught, which will be the case 99% of the time. So let me ask you guys a question. How does this compare to the voltage gain of our common emitter core amplifier? You have notes? Ostensibly took them. So exact same magnitude, opposite sign. So the common emitter amplifier is an inverting amplifier with a gain of Gm times R naught in parallel with RC. Our common base amplifier is a non-inverting amplifier with a gain of Gm times R naught in parallel with RC, except. So they have the same gain characteristics, at least at the core level. Just one of them inverts the signal, the other one does not. Okay. All right, so our voltage gain is taken care of. Now let's look at our input resistance. Actually, before we do that, if, this is just a quick aside thing here. Let's say that I had emitter degeneration as well, right? So I originally had some resistor here, RE, that would manifest in our small signal model as some resistance here, RE. Would this resistor have any impact whatsoever on our voltage gain? No, because it's directly in parallel with the input voltage that we are applying, right? So degeneration isn't going to have any impact whatsoever on our voltage gain relationship, just as a heads up here. Okay, that's something useful to note. Now let's determine Rin. So we're effectively, let me write this out. Let me use the right color. We're going to be looking at the exact same circuit for the most part. So our small signal model should look something like this. R pi, V pi, GM V pi, R naught. Here's our test voltage, V test. Here's our test current, I test. Here's my resistance RC. And now I'm going to call this nodal voltage up here VC with respect to ground. So once again, just like we've done every other time we're trying to find the input resistance, we're just going to find the ratio of V test and I test, and that will be our Rn. Okay. So once again, we can observe that V test is nothing more than negative V pi. And this time we're going to do things a little bit differently. We're going to apply KCL at our emitter node. So we're going to say that this current I test flowing in is equal to this current plus these two currents. So let me just write emitter, collector, and base. So KCL at our emitter yields us I test is equal to V test divided by R pi. That's the current flowing up through the resistance R pi. Then I'm going to have this current right here flowing up. So that's going to look like negative GM V pi. So negative GM V pi is going to be the same thing as positive GM V test. And then lastly, I'm going to have V test minus VC over R naught. Okay. And now we're just going to manipulate this a little bit. So we'll have V test times a factor of 1 over R pi plus 1 over R naught plus GM minus VC over R naught. And this is going to look like V test divided by R pi in parallel with R naught in parallel with 1 over GM minus VC over R naught. We all okay with that? Okay. Now we're going to apply KCL at our collector. And so this is going to look like, somebody needs to mute themselves. Negative GM V test So that's this current flowing down through the dependent source. Then I'm going to have the current flowing down through the resistor R naught. So that's just going to be VC minus V test over R naught. And lastly, I'll have VC over RC is equal to 0. So I can rearrange this guy to find that V test times 1 over R naught plus GM is equal to VC times 1 over R naught plus 1 over RC. And rearranging VC just looks like V test times R naught in parallel with RC over R naught in parallel with 1 over GM. Expanding this out, we're going to have VC is equal to GM R naught RC plus RC divided by R naught plus RC. So this is equation 2. Up here is equation 1. And now I'm going to substitute these two into each other. And again, just give you the results because the algebra here doesn't really teach us anything important. So substituting equation 2 into equation 1 gives us the relationship I test is equal to V test over R pi in parallel with R naught in parallel with 1 over GM minus V test over RC times GM R naught RC plus RC over R naught plus RC. And skipping multiple algebraic steps, our input resistance is just the ratio of V test to I test, which will come out to be R pi times R naught plus RC divided by R pi plus 1 plus beta R naught plus RC. So for our base common emitter amplifier, our input resistance that we saw was R pi, which is small-ish in terms of resistors. Well, now we have some number divided by R pi plus a really large resistance, right? 1 plus beta times R naught is going to be much larger than either of those two guys. So we wind up having a very small input resistance with the common base amplifier. So for applications where we need a small input resistance, this is the one that we would typically use. That's one of its defining characteristics. Now, let's look back here. What do you think would happen if we had emitter degeneration? So if I were to put a resistor right here, how would that impact things?
Have another turn here.
So let's think about things really quickly, right? So without this guy here, I see the ratio of V test over I test was equal to the input resistance that we just found. Now, all this resistor is doing is just stealing a little bit of that current away effectively. So this resistor RE is in parallel with this voltage source, which means it's in parallel with the input resistance we just determined. So we wouldn't need to do any analysis whatsoever. We can literally look at this and say, because this resistor is in parallel with RE, and we just found the equivalent resistance of this whole other thing, we just have RE in parallel with the equivalent resistance of the whole other thing. Okay. Without having to do any new analysis whatsoever. Okay. Let me sneak this down here in blue. If VA is equal to infinity, so if we neglect the early effect, then Rn just becomes R pi in parallel with 1 over Gm. And I know you're thinking, well, where the hell does the Gm even come from? Remember that beta is defined in terms of Gm and R pi. So it got lost in the manipulation algebraically to get this into a smaller form, but it'll work out to be that. So there's our input resistance. Our output resistance, you guys are either going to love or hate this. So to determine our output resistance, I'm going to draw not the small signal model first. So here's our VCC. Here's RC. This is some DC voltage. Because we're finding output resistance, we short circuit our input terminal, which is the emitter in our case, and we're looking in to here. I argue that we've already done this. So what I mean by that specifically is from a small signal perspective, we have this circuit where the emitter terminal is at ground and the base terminal is at ground. That is the exact same thing, or the exact same circuit that we analyzed when we were looking at the common emitter amplifier's output resistance. Because when we turned our base terminal to ground to turn off that input voltage, our emitter terminal was already at ground. So there's really no reason for us to analyze this again. We've already seen it before. So whatever our output resistance was for the common emitter amplifier core, we have the exact same output resistance here because we have the exact same conditions occurring to the circuit. So we're going to get to a point where we're just starting to rehash things that we've already seen. And if we're smart enough to realize we've already seen it, we don't need to do any analysis again. So for here, I can literally just say R out is equal to R naught in parallel with RC, and I'm going to put a note, same as common emitter amplifier, because that's where we initially analyzed that circuit. Are we okay with this? Why waste time reanalyzing things we already know? Okay. So there's our output resistance. So let me double check something here really quickly, just to make sure I'm not telling tales out of school. All right, so now I want to look at the common base amplifier, but what if we have some base resistance, right? So what if there's a resistance seen between the base terminal and the application of our DC biasing voltage, which would be very representative of what that voltage divider circuit is going to look like as a Thevenin equivalent circuit, right? So common base with base resistance. Okay, so this is the circuit that we're looking at. I'm just going to call this guy RB, like so. Oh, and this technically shouldn't be grounded. It should be some DC voltage. It's just going to look like an AC ground. I'm going to draw my small signal model for this. So here's my resistance RB. Here's my base terminal. Here's my resistance R pi, across which I have the voltage V pi, excuse me. Here's RC, V out, collector, emitter, VN. So extraordinarily similar small signal model, because the only change that we made is we now have some resistance RB between the base terminal and ground instead of just having the base directly wired to ground. So for our voltage gain, we're going to analyze this guy directly. What can we say about the relationship between Vn and V pi this time? It's a voltage divider. Absolutely right. So I think that V pi is going to be negative Vn times R pi over R pi plus RB. Everybody okay with that? And so now I'm going to do the analysis just like I did a while ago, except I'm going to use this relationship everywhere I see V pi. Okay. So KCL at my collector. is going to look like, so the first thing that I would see is GM times V pi. So that's going to look like negative Vn times GM R pi over R pi plus RB plus V out minus Vn over R naught plus V out over RC is equal to 0. And now I'm going to lump things together. So here's my coefficient for Vn on this side. So what's GM times R pi? Let's have notes. Beta. So this is going to look like beta over R pi plus RB plus 1 over R naught is equal to V out times 1 over R naught plus 1 over RC. And now all I'm going to do is make these guys have a common denominator so that I can add those fractions together. So that's going to look like Vn times R pi plus beta R naught plus RB over R naught times R pi plus RB is equal to V out divided by R pi in parallel with RC. And from this, our voltage gain then becomes R pi plus beta R naught plus RB times R naught in parallel with RC all over R naught times R pi plus RB. And this will be approximately equal to beta R naught in parallel with RC over R pi plus RB. Or, let me put this here. For VA is equal to infinity, our voltage gain reduces to beta RC over R pi plus RB. Any questions about the voltage gain there? Bless you. Okay, pretty straightforward. So now let's determine Rn. I'm going to be lazy here. Drop this bad boy right here. So here's our I test. I think I used lowercase I last time. I'm gonna ask you guys a question. This is a real time. What's the difference in this small signal model than the one we saw the last time? RB exists. And how is RB connected? In series with RPi. So we go back to all of this math. What's that going to change? Every time we see RPi, we replace it with RPi plus RB. Done. Why make it harder than it needs to be? By inspection, Rn is equal to, close that, RPi plus RB times R naught plus RC over RPi plus beta plus 1 R naught plus RC plus RB. No need to do any new work. For including the early effect, so, or neglecting the early effect, for VA is equal to infinity, Rn reduces to RPi plus RB over beta plus 1. Output resistance. Let me ask you guys a question. Let's go back up here to where we determined R out here. If we put a resistor between here and here, is that going to change? Not at all. No analysis whatsoever. Why? We don't need it. R out is equal to R naught in parallel resistor. So we're ready to, Anna, do you have a question? What is it?
For the R out.
Mhm. So let's talk about that one too. Let's talk about that here in a moment, where we look at the fully biased circuit. Okay, we'll see what effects that'll have. So we'll go back to our fully biased circuit that we had previously, right? So let's start here, which is exactly what I had drawn originally. So here's R1. Here's R2. Here's RC. Here's RE. So this is where we're formally looking at what the emitter degeneration does. C out. RL. V out. UCC up here. C in. R sig, and Vn. Okay. So I'm going to redraw this white. Okay. So the one thing that I can notice very easily from the jump is that since VCC looks like AC ground for our small signal model, I'm going to have a resistor R1 in parallel with R2 between my base terminal and my AC ground. So that base resistance RB that we just looked at is just getting replaced by a resistance R1 in parallel with R2. Okay. So if this is my transistor portion, now I have a resistance here that's R1 in parallel with R2. And then, like I said, that bit right there is going to be AC ground. Okay. Our output capacitance is going to look like a short circuit because we're choosing a large capacitor to capacitively couple our load to our circuit. So if this capacitor small signal looks like a short circuit, then RL is connected between the collector terminal and ground, and RC is also connected between the collector terminal and ground. So I'm just going to see RC in parallel with RL between the collector and ground. Here is my output node. Now let's see what's going on over here. So I have a resistor connected between the emitter terminal and ground. And I have a resistor R sig connected between the emitter terminal and my input voltage. So this is, let me put, this is V sig, not Vn. Okay. So this is a simplified representation of what our fully biased network looks like. You already know how everything I just circled in green works. Right? So in all of my previous relationships, everywhere I saw RB, I could just replace it with R1 in parallel with R2. And all of my previous relationships, everywhere I saw RC, I could just replace it with RC in parallel with RL, with doing no extra work whatsoever. So the only thing we have to do is figure out what's going on right here. Well, this is just a voltage divider, yet again, right? So effectively what we have is something like this. So here's V sig. Here's R sig. Here's RE. And then these terminals that I'm putting right here is where the equivalent circuit of my transistor amplifier part goes. So here is what I'm going to call Rn prime. AV prime times Vn. R out prime And here's V out. I want to be clear here. I've already lumped the RL in to my output resistance. If I didn't do that, I would see the RL across these terminals, but it's going to come out as the exact same relationship. So instead of formally doing that, I'm doing it effectively by inspection by saying, everywhere I had RC previously, I'm replacing it with RC in parallel with RL. So it's already taking that part into account. And now my output voltage is just an open circuit voltage between the collector node and ground. So with this guy right here, we can now figure out how the emitter resistance impacts all of these things formally, where we earlier were just saying it should look like this, right? We can very easily see now that our emitter resistor is just in parallel with the input resistance of the transistor amplifier network, right? Okay, so let's look at our voltage gain first. Our voltage gain, like we've done previously, is just going to be the relationship between V out over V in times V in over V sig. So looking at just this part right here, what's the relationship between V out and V in? AV prime. Just this circuit here, right? So V out is going to be equal to AV prime times V in, because there's not going to be any voltage drop across that resistor R out because it's open circuited, right? So V out is equal to this, divide by V in, and all we get is just that AV prime. So going back to our previous notes on the common base amplifier with a base resistance, that part is just going to be approximately beta times R naught in parallel with RC. But now we don't just see RC. We're going to have RC. Everywhere we had RC, we replace it with RC in parallel with RL, right? So that's going to be RC in parallel with RL divided by R naught, excuse me, R pi plus RB. So scrolling back up here, how are we going to find the relationship between V sig and V in? It's a voltage divider. Yep. So it's going to look like RE in parallel with RN prime over R sig plus RE in parallel with RN prime by inspection. Don't even need to do any analysis whatsoever, right? And then because Rn prime is not a horrifying relationship, but kind of big. I can write it out here. So this is going to look like RE in parallel with R pi plus RB times R naught plus RC all over R pi plus beta plus 1 R naught. I'm a stylus. There we go. Plus RC plus RB. Close that off. Divided by R sig, and because I don't want to write all that down again, I'm just going to put plus the numerator. Yes, James. R1 in parallel with R2. Yep, so I'll put it in here. That's easy enough. And I'll do it here as well. Thank you for that. Yeah. So everywhere we saw RB previously, we're just replacing it with R1 in parallel with R2. I just missed that. Thank you, James. And then our overall voltage gain would be, we just multiply these two things together. Yes, North.
Go back to the first time we wrote RN, I don't have a limit here, but R not.
So the very first time that we wrote it, was right here. The second time that we wrote it, when we had a base resistance, we replaced R pi with the quantity R pi plus RB. So we definitely should have parentheses around things. So what is the input resistance seen by V sig here? Yep, that's it. So R sig plus RE in parallel with RN prime. I'm going to leave it as that because that's literally just the denominator from here. No need to rewrite all that jibber jabber out. Now, Hannah, to answer your question. If we turn off our signal source, what's the output resistance that we see? R out prime. So that's going to be R naught in parallel with RC in parallel with RL. Yes, ma'am. We do. Thank you for that. So this is just getting bigger and uglier. RC in parallel with RL. What is that? R naught plus RC in parallel with RL. Thank you for that, because that is technically correct. Do we need to analyze the MOSFET load, which is the common gate amplifier? Why? Everywhere we saw R pi, just replace it. Well, I guess that's actually going to be impactful. So let's take a look at it. Actually, let's not, because I left those notes upstairs. So that's what we'll do at the beginning of class on Friday. Today, Wednesday? Yeah, beginning of class on Friday. So I just want to give you guys fair warning. We are ripping through this material faster than I had intended. Oh no. So you might just have time to study during finals week. Bet you're going to be real upset about that. Yeah. I had meant to do it yesterday and then got wrapped up doing stuff. No, it needs to be a thing. It definitely needs to be a thing. The sooner I get it, the more time you have to do it and all that kind of stuff. If I'm being realistic, I hope to get it done tomorrow. It will definitely be up by the time we get back from Mardi Gras break, for sure. Still, that's just waiting on me as well. So, yeah. Yeah. So I'm gonna put homework sets up on this material. So there'll be like one homework set for common emitter / common source amplifiers, one homework set for common base / common gate amplifiers, one homework set for what are called emitter followers and source follower amplifiers, which is this common collector, common drain. It's just got a different name for reasons that I'm not really sure. Anyway, I think we're getting to the point where, and most of you guys are probably used to this, where I just dump a whole shitload of homeworks and stuff like that on you at one time and just say it's due at the end of the quarter. We are pretty much there, even though the end of the quarter is about 3 weeks out. I think that's just the sanest way for me to do stuff. So
for testing material, would we have to analyze the circuit, like take out the small signal diagram and analyze that way, or we won't have to?
So we give an equation sheet where I just give you the common emitter base, common emitter base with emitter degeneration. Like I give you the building blocks and then I ask you to analyze the full scale circuit, which is what we've been doing here at the end, kind of thing. Yeah, so nothing real wild or crazy. Yep. Just take the building blocks that we know how they work, chain them together correctly, and do elementary circuit analysis, and you're good to go. That's all this material needs to be. Send me an email, because that one I know I have the MOSFET part made out already, and so making the BJT part should be pretty easy, because I just need to go in and, you know, I've got all the notes, just type that shit up. Yeah. So, yep, getting through material too quick. Oh no. Sorry, I'm too good. All right, I'll see you guys later.